Welcome to Spring LIB.
In order to predict the valence electron molecular orbital configurations for the following ions, we need to figure out which molecular orbital diagram corresponds to each of them. As you know, there is a switch as you go from left to right across the periodic table. For sodium, anything in group 1A, it's going to be sigma, sigma star, and then sigma 2p, pi 2p, pi 2p star, and then sigma 2p star will be the order. We now need to count up the number of valence electrons. Or let me back up. This is actually the molecular orbital energy diagram for anything that is a noble gas. And sodium, although it has one valence electron, with two sodiums and a 2+ charge, that one valence electron has been removed. So the electrons that are left should then follow the noble gas molecular orbital diagram configuration. And with all of the electrons removed from sodium, then this is going to look something like this, where it's isoelectronic with neon 2. The bond order is going to be 1/2 the bonding valence electrons minus the ones that are star, the anti-bonding. So it's going to be 8 minus 8, or 0. So this will have a bond order of 0, and it will be unstable. To be stable, we need to have a bond order of at least 1/2, preferably 1 or greater. Now for the next one, we have magnesium 2+. So its molecular orbital diagram energy will be sigma 3s star, pi 2p. You'll notice that these two are switched. There should be a diagram in your textbook that shows on which side of the periodic table we have this configuration, and where the crossing point is around oxygen, where we have this configuration. So for magnesium 2+, we're going to have a total of just 2 valence electrons. When plugging the 2 into the sigma 3s, we're going to have just 2 bonding electrons, 0 non-bonding. So we have a bond order of 1. So this would be stable. For the next one, we have aluminum 2+. So it'll have the molecular orbital energy diagram similar to the one we just did. We're in the third period, so it'll be 3s, 3s star, and so forth. Aluminum 2+ has each aluminum with 3 valence electrons, but 1 is removed, will give us a total of 4 valence electrons. We plug in the 4, we have 1/2 2 minus 2, 2 in bonding, 2 in anti-bonding, and we get a bond order of 0, so it would be unstable. Now for the next one, we have silicon 2+. Silicon is still on the side of the periodic table that has this arrangement rather than this one. Silicon has 4 valence electrons. There are 2 of them, that's 8, but we have a 2+ charge, so minus 2 gives us 6. We plug in all 6 valence electrons, 1, 2, 3, 4, 5, 6. According to Hund's rule, we're going to singly occupy the degenerate orbitals before doubling up. So bond order will be 1/2, 1, 2, 3, 4, minus 2, which gives us a bond order of 1, so this is stable. Now we move on to phosphorus. Phosphorus still in period 3, row 3, so we're using the sigma 3s star, and so forth. And phosphorus has 5 valence electrons. There are 2 of them, that's 10, but it's a 2+, so 2 are removed. So that's now 8 valence electrons. We plug in all 8. 1, 2, 3, 4, 5, 6, 7, 8. We're going to have 1, 2, 3, 4, 5, 6 that are bonding, so 1/2 6 minus 2 gives us 2. Bond order of 2 is stable. Now for the next one, we've got sulfur 2, 2 plus. This is now where we have the switch, and now these two switch places. So we're going to have our sigma 3p come before our pi 3p. And sulfur has 6 valence electrons. There are 2 of them, so that's 12. But because it's 2 plus, it's now 10. 12 minus 2 is 10. So we'll plug in our 10 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we have 1, 2, 3, 4, 5, 6, 7, 8 bonding, 2 anti-bonding. So it's 1/2 8 minus 2, which gives us a bond order of 3. So this is definitely stable. Now for the next one, we have fluorine 2, 2 plus. We're still going to have the same electron configuration, molecular orbital energy diagram as we had before. And fluorine has 7. There are 2 of them, that's 14. But we take 2 away because of the 2 plus charge, so that's 12. We plug in all 12, and we get this. So we have 1, 2, 3, 4, 5, 6, 7, 8, minus 1, 2, 3, 4. 1/2 8 minus 4 is 2, so this is also stable. Again, anything with a bond order of 1 or greater is going to be stable. Now for the last one, we have argon 2, 2 plus. We're on the same side of the periodic table, so it's going to look the same as we had before. Now on the right-hand side of the periodic table, argon has 8 valence electrons. There are 2 of them, so that's 16, but it's the 2 plus charge, so minus 2 gives us 14. We plug in all 14 valence electrons, and then we have a bond order of 1/2 8 minus 6, which equals 1. So this is also stable.